What I'd like to do is to start it out and ask if there's any questions. I think there were some questions. I wanted to make sure that you got them answered. And if there are none, that's okay. That's fine.
I have a question.
Okay.
Regarding the homework, there was some homework for last day, and are we supposed to send it to you each day or at the end of the chapter?
No. I have not assigned that officially yet.
Okay.
I will assign that next. So that's good. I'll always assign orally the homework. Okay.
Okay.
Yeah, you
Thank you.
won't. I won't surprise anything. I won't surprise you with anything.
Well,
what's that?
When you orally assign the homework, will you also assign when it's due, or is it generally going to be due like the whole chapter will be due together?
No. I will assign it piecemeal.
Okay.
Okay. So let me, in fact, go over that right now. I'm going to share my screen since that seems to be the concern. Let me share my screen and go to the sheet. This is the main sheet. No, I can't do that now. I'm working. That was my granddaughter. My granddaughter came in and she doesn't know that I work for a living. Okay, so this is the sheet. I did want to point out a few things here. Number one is kind of the assignment. Right here is the address for the YouTube of the video of last lecture. So if you want to brush up or you need something to fall asleep with, you might open it and watch that. Okay. Yes, go ahead.
So
I tried clicking it earlier and it told me that it's private.
yeah, I got the same thing.
Okay, I will take a look at that and I will update that to make sure that it isn't private, that anybody with the address. So thank you for letting me know. Now, there are reviews. As I mentioned in the book, there are assigned problems, and many times the solutions are given in the book. I'm going to assign those, and we're going to talk about them if you want to. You are going to be responsible for them, but you know, I don't want, if they're so obvious that we're not going to be talking about them, then let me, you know, then I don't want to waste the time. So let's look over the review. Chapter 2, okay, problem 3. Okay, this is way up here. I don't know why I'm all the way up here. Okay, excuse you getting dizzy as I find the chapter here. Woo, this is a big book. It just goes on and on and on. Okay. Yeah, here we go, chapter 2. Now, this is a very interesting problem. Are you ready for this? The answer is yes, you're ready for this. I don't think that this will write on here. No, it doesn't. Okay. Let's look at this. This is very fascinating. You can see my cursor, right? The derivative of n squared is equal to 2n. Is that correct? Nod, yes, okay. But the derivative of n squared is the same thing as the derivative of n times n, correct? But n times n is equal to n plus n plus n times. And so the derivative of each one of these is 1. So the derivative of the first one is d sub dn of n is 1. Of the second one is 1. And how many 1s do we have? We have n 1s. This d sub d, oh my gosh. I never noticed that before. This d sub dn should not be there. This is simply equal to 1 plus 1 plus 1 plus 1, correct? And this is equal to n. Now, you might have seen this before because I share this problem a lot. It's a very interesting problem, and you might be looking at it and thinking, what does this have to do with multidimensional signal processing or Fourier analysis? Actually, it does have something to do with Fourier analysis, and clearly something's wrong here. Do you agree with that? Because up here we said the derivative was equal to 2n. Down here we have n, and it can't be both of them. How many have seen this before? Okay, Adam and Glauca. Oh, three of you. Okay, so I will ask you that haven't seen it before to try to figure out what the heck is wrong with it, because this is one of the most perplexing problems of finding what the derivative of n squared is. It's one of those curious ones where you prove that 2 is equal to 1 and weird stuff, and you got to go back and figure it out. So I want you to think about it. Okay, those of you who've seen it before, who can explain what the problem is? Maybe we don't want to waste time further on this, and you can explain it. Okay, Justin, did you raise your hand, Justin, or were you scratching?
I have not seen this, so I'm not sure what the problem is.
Okay. Okay, David, go for it.
Okay. So as we go from the second, or as we go from the first line where we have n times n to the second line where we have n n's added together, we turn one of the n's from a variable into a constant, and then we forget that it was a variable.
No, that's not the reason. That's not the reason. Let me explain you what the reason is. Anybody else want to try at it? No, David, not turning a variable into a constant. It's not what I'm looking for, and it's not the answer here. Anybody else want to give it a try? Okay, Adam, go for it.
Oh, it's because when you have n times n, that's continuous, and then you can't just break it down into being discrete by adding n plus n plus n plus n plus n.
Yeah, that's exactly right. In fact, let me go here, and this is for another presentation that I was giving today. So just ignore the Bradley Center stuff. I'll just get rid of that. I need something on which to write. We must remember the difference between discrete time and continuous time signals. And when we have a signal, here I go again. Okay, I got to get a better background than just white, because white doesn't show. Okay, that's for me to do next time. So here's the idea. If you have a signal that looks like this is a discrete time signal, right? If I can get this correct. That's a discrete time signal. What is the derivative at this point? The derivative of that point doesn't exist, right? The derivative doesn't exist there. There's no concept of a derivative in a discrete time signal. The closest you can get is something like a first distance, you know, one element minus another element. That's kind of a derivative, but it isn't a derivative. So when we say we want the derivative of n squared, we are really asking for a function which looks like this. If I plot n squared, I get kind of a sampled parabola. And I'm asking for the derivative of this thing. The derivative does not exist. This would be x sub n. This would be a discrete time signal. And we are asking for the limit of, what's the definition of a derivative? N plus delta n minus x sub n over delta. Isn't that the definition of a derivative? I'm sorry, just x plus delta, just forget the n. And we want the limit of this as the increment goes to 0. Isn't that the definition of a derivative? But if we look at this, what is this? What is that delta? You cannot have a delta in discrete time signals. You can't have something which ultimately shrinks to 0. So the whole premise is flawed. And David was pretty close. He was pretty close, but no, that's not the situation. So that's the answer to this. The idea of a derivative of a continuous or a discrete time signal is ludicrous to even think about. Okay, let's go back and look at the other problems and see if we can figure out what those are. So that's the solution to the first problem. The other problem that we had was problem 19. So let's take a look at problem 19. And I'll give you a hint on this one. Okay, here's problem 19. It's very, very similar to what to the problem that I gave you. Let x of t be causal. Do you remember what causal is? Causal is 0 for negative time. What are the even and odd components of x of t? Well, that's actually very simple to calculate because I gave you the formula and it's just kind of a plug and chug. But the next one's a little bit more interesting. Specify part B in 219 says specify a function that is both causal and even or causal and odd. Does there exist a causal function which is even or a causal function which is odd? Think about it and see if you have a response. Anytime you see something weird that puzzles you like this, think of a degenerate case. Okay, David, what is it?
Both of those would be x of t equals 0.
Yes, that's exactly right. If x of t is equal to 0, you have a causal function. It's kind of a degenerate case, right? But it's also an even function because if you take 0 and you flip it around, you get the same thing. It's also odd because if you take 0 and you flip it around this way and then flip it around this way, you still get the same thing. So that's the only answer there. So the next question. So we're getting these relatively easy, I believe. The next one is problem number 20. So let's look at problem number 20. Is an odd function evaluated at the origin always 0? Always. Any bites?
Yes, it is always 0.
It is always, because the idea, well, here's the idea. Whoops, that doesn't work. Yeah, it is, because if you have, now why does my cursor look so beautiful there? If you have any sort of odd function, remember what an odd function looks like. That means that an odd function as a function of time is equal to minus an odd function at minus time. Now, we really haven't gone through this, have we? In fact, I'm giving you a non-causal homework problem. I'm giving you the problem before we've covered it. But let's take a look at it anyway. This is what an odd function is. So an odd function looks like this. And so if you flip it around this way, and then you flip it around this way, you get exactly the same thing. So it always has to be 0, because if it's not 0 and you flip it around, say it's this point, when you flip it around 2 times, you're going to get this number. So you don't get exactly the same thing. So we'll talk more about this as we talk about even and odd functions just in a second. Okay, the other problem, let's see what the other problem is. I'm sorry, that was a non-causal problem. I should have talked about the even and the odd first. The next question is equation 54. Not equation 54, but problem 54. So let's go down to 54. This is a very interesting problem. I think it's a very interesting problem. This is x of t is equal to t to the minus 3/4. There's a reason that I chose this very easy, weird function. First of all, notice at the origin, it's always infinite, correct? And what we can do is we can compute both the area and the energy over the interval, as you can see, the interval from 0 to 1 and over the interval from 1 to infinity. And what you're going to find out here is something just fascinating. In one case, you have infinite area and finite energy. In the other one, you have infinite energy and finite area. So one does not imply the other. If you go to Lebesgue measurable, however, the Lebesgue measurable has to be measurable everywhere. You're not allowed singularities. So this doesn't work if you're Lebesgue measurable. And one is actually subsumed in the other one. But for this example, you get that area is not equal to energy. And this is what is shown in B. Okay. So I think we've kind of covered that. You know, we've gone over the sketch. I'd like you to look at this, and then if you have any further questions next time, we can talk about it. Now, I would like you to do problems 1 and 2 and look at problems number 1 and 2. When I talk about problems number 1 and 2, I'm talking about at the homework slide. Where is this now? Yeah, here it is, homework on Google Docs. So you click on that, and hopefully you go to the homework slide. So let's try there. Now this is very similar, and we'll ask this next time, and I'll call on you randomly next time. And the way we'll do it, we have 6 people here, so I can flip 3 coins, and I can choose you randomly from 0 to 6. Is there any periodic signal with finite energy? I don't know, anybody want to hazard a guess here? Okay, Glauca?
I think there is only one kind of periodic signal with finite energy.
And that is what?
That's the delta function, the impulse.
Let's see, a periodic signal. No, it has to be periodic. The impulse is not periodic.
But if you have many impulses with
Yes.
a period, the impulse it's only 1 point. So
no, in fact, when we get to the impulse, we'll find out that the impulse, or the Dirac delta, as I like to call it, has infinite energy. So that's not the right answer.
Would just 0 satisfy it?
There you go. Same answer as David gave before. It's kind of a degenerate case, but that's, yeah, I believe that's the only case. Are all finite area signals bounded? We literally answered this in the lecture last time.
Yeah. Yeah. No. There's the let's see. Logarithm.
Well, there's the logarithm, and plus, if you go back to this problem, you'll find out that it is that this problem might answer that question also once you work this out. By the way, the answer to this problem is given at the end of the chapter, so you can take a look at it there. Okay, let's try another one. I got so many. I'm one of these guys. You can probably see my screen. I have 1,000 windows open. Okay. And are there finite area signals that are finite energy? This, in fact, is answered by that problem that we pointed out in the book. So that's already answered. Second question is, let it be causal, C of t times U of t. Now, why do we multiply it by mu of t? Mu of t is the unit step. We multiply it by mu of t just to explicitly state that if there is anything happening for negative time, the mu of t, which is the unit step, just chops off everything for negative time. That's what that mu of t does, and it does it very nicely. Can any periodic signal be causal? We answered that. Can find the even and odd components of C times mu? That was a question in the book. And then sketch the even and odd parts for the causal function e to the minus t. I'd like you to do that. Okay? And we haven't covered even and odd, so let's go through and cover even and odd if you haven't, since we didn't talk about that. So let me go to chapter 2 and let me talk about even and odd. Where do we go? Where do we go? There we go. So here's the idea of even functions. And again, we talked about it and I didn't properly introduce it, but an even function is a function. You know what? I found out that if I'm not full screen, I can draw better. So I'm going to go ahead and do this. Can I close this? Yeah, I can close that. Make it a little bit bigger. Okay. So this works much better. So an even function is a function which looks like this. Well, I tried to make it even. So this is an even function. And an even function means if you look at it in the mirror, if you look at the function in the mirror, it doesn't change at all. Or equivalently, you can flip it around. You can take t and you can make it into minus t, and it doesn't change anything at all. So it's even. So that's a concept which is important. An odd function, as we talked about, is a function which has symmetry, and if you flip it over in one direction, flip it on the y-axis, and then you flip it on the x-axis. So here we only flip it on the x-axis, the t-axis. Here we flip it on both the x and the y-axis, and we get the same thing. That is said to be odd. Now, there's lots of interesting properties concerning even and odd functions, and there is a table in the book that has many of these properties. Let's talk about some of these properties. One of which is something very interesting, is that every function in the world, this could be an arbitrary function. Any function in the world can be written as an even function plus an odd function. If you give me any function, you give me, I can give you an even part and an odd part. By the way, I probably should have said over here that an example of an even function, let me backtrack here. An example of an even function is the cosine of t. Because the cosine of t, and again, I like to think geometrically, the cosine goes like this, right? Well, if I could draw well, it would go like this. And the cosine of t, if you flip it along the x-axis, you get exactly the same thing. An example of an odd function is the sine of t. And the sine of t is something which is like this. I'm glad you guys have had trig before, so you can know what it is. So therefore, if you flip it on the x-axis, then you flip it on the y-axis, you get exactly the same thing. Does that make sense? Okay. So those are examples. Again, any even function, or any function, C of t can be any function in the world, can be written as an even function plus an odd function. And here's the cool thing. You can figure out the even and the odd function from the original function. You find out the even function by taking 1/2 of C of t, and then you flip C of t around to get C of minus t, and you take half of that, and that's the even part of the function. And then the odd part of the function is you take C of t and subtract the transpose. The transpose, by the way, is a fancy way of saying you take the function and you flip it along the x-axis. That means you transpose the function. So C of t plus C of minus t, if you add those two together, you get an even function. And if you take the function and then subtract the minus t, you get an odd function.
Yeah. You mind if I ask a question here?
Okay.
Yeah. You've defined odd as something that you can flip over the x-axis and the y-axis and get the same thing.
That's correct.
Yeah. Is there a reason you prefer that over rotating it 180 around the origin?
No, if you rotate at 180, if you rotate at 180 around the origin, let's see, I guess you do get the same thing. So this is like a lot of things. Do you ever notice what's the definition of cosine of t? We'll talk about this later, but what's the definition of cosine of t? I don't know. You could define it by a Taylor series. You could define it by an integral, a solution to a differential equation. There's a bunch of ways to figure out and define what the cosine of t is. So I think that's probably true for any definition. This is the definition that we chose to use here. Now, David, you gave an equivalent definition. And so if you're better at thinking that way, I mean, that if you're more in tune of thinking that way, that's fine. That's fine. I like thinking about it as flipping around the x-axis and then the y-axis, and you get exactly the same thing. But they are equivalent. Okay. Let me show you the classic example. You know what the classic example is? The function c of t. Let's see if I can get this up here a little bit more. Is equal to e to the jt. That's a nice function. Well, this function, according to our theorem, has an even part and an odd part. Guess what the even part is? Well, if we take this equation, the even part of e to the jt is equal to 1/2 times e to the jt plus e to the minus jt, right? Hopefully, if you look at that, it rings a bell. What is that equal to? That's equal to
sine, isn't it?
Cosine.
Cosine.
It's equal to the cosine of t. And as we've talked about before, the cosine of t is an even function, right? And what is the odd part? The odd part is equal to 1/2, or let me write odd here.
Is it J sine?
Yeah, yep, you're right. But let's, 1/2 times e to the jt, you got it. Minus e to the minus jt. And who said that?
It's Justin.
Okay, Justin. Yeah, you're exactly right, Justin. This is equal to j times the sine of t. And as we mentioned, sine is an odd function. And we have just derived Euler's formula. E to the jt is equal to the even part of e to the jt plus the odd part of e to the jt. So this is kind of a classic example of decomposing an arbitrary signal into its even and odd components. And you can see it's a very powerful concept. Okay, let's see if I can get rid of this. Nope, that doesn't work. Oh man, this is going to take a long time. Let's see if I can grab a bunch of it. Well, that's okay, but I got rid of some of my notes too. Let me ask you this. Here's a couple of interesting things that we can do. Suppose we had the integral from minus infinity to infinity of e to the minus t squared times the cosine of t dt. How would you evaluate that integral? You could evaluate it by going to Wolfram's. Wolfram has this new page where he evaluates integrals. But let's do a little bit of working here. Let's do a little bit of thinking. If you take an odd function and you multiply it by well, let's take even first. If you multiply an even function by an even function, do you get an even function? Yes. What about an odd function times an odd function?
That's even also.
Yeah, you get an even function. If you multiply an even by an odd, what do you get?
Odd.
You get an odd function. So it's almost like an exclusive OR, right? Because if you take an odd function and multiply it by an even function, you clearly get odd. So it's kind of like an exclusive OR in that way, right? It's the same truth table as an exclusive OR, kind of interesting. So with that, let me do the following. If we have an even function and we integrate over, say, from t is equal to some value, say minus t to t of an even function, well, you notice that if it's an even function, then the part for positive value is the same as for the negative value. So I think you can see immediately that this is the same thing as just integrating from 0 to t. It's geometrically obvious, right? Taking the integral over only 1/2 of the interval and multiplying it by 2, right? That's kind of obvious. What's more interesting is if you take the integral of t is equal to minus t to t of an odd function, what do you always get?
0.
You always get 0, right? Because if you have an odd function, it comes up here and it's odd about the origin. I got to get it through the origin. Okay, so you see the idea that this part eats up this part and we're left with 0. So does all this make sense to you? If it does, let's go back up here. E to the minus t squared, even or odd?
It's even.
Yeah, e to the minus t squared is like a Gaussian, right? It kind of looks like this. It's the classic bell-shaped curve. And the cosine of t is equal to something. But this is the same thing as twice times the integral from 0 to infinity of exactly the same integrand dt. Do you agree with that? What I think is more interesting is if we do, let me get rid of some of this. Let me get rid of you. Okay, you want to get rid of the whole thing. That's okay. Okay, computer thinks it's smarter than I am. Suppose we have the integral from minus infinity to infinity of exactly the same thing, e to the minus t squared times the sine of t dt. What's that equal to? Can you tell just by looking?
It's 0.
It's 0. Why is that? Because e to the minus t squared is even, the sine of t is odd, and even times an odd function is equal to an odd function, and the integral over symmetric limits of an odd function is equal to 0. So I don't have to do any work here. I remember taking a course in quantum mechanics, and I had all these crazy integrals, and I finally figured out that it was an even and odd sort of thing. And if I did this properly, I could evaluate the integrals very, very easily. So this is equal to 0. Does that make sense? So therefore, we have even and odd. Okay, let me ask you another thing. Shoot. What's the derivative of an even function?
It's an odd function.
Is it an odd function?
Yeah.
And what's the derivative of an odd function? Turns out to be an even function, doesn't it? And what's the derivative of an odd function times an even function?
An even function.
Okay,
It's the derivative of an odd function. So
what is odd times even? Odd times even is odd. So we're taking the derivative of an odd function, which must be an even function. So you can see there's a lot of mileage we could get out when we think about even and odd functions, when it's appropriate to think about even and odd functions. It's a tool for your tool chest. It isn't something that answers all questions, but when you come up with it, come up to problems like this, it's going to be very useful. Okay, this brings us now to the Fourier transform. That's the new topic that we're going to talk about. This is the definition of the Fourier transform. I said a little bit about this beforehand, and you can see that I don't use an e to the minus j omega t. And let me repeat why, because I don't know what omega is. I don't know what 100 radians per second means. I don't. If I see 100 radians per second, I divide by 2 pi and figure out how many cycles per second it is. So omega is kind of, transparent and ugly. So therefore, I like to use explicitly omega is equal to 2 pi u. One of the reasons is that the u is more intuitive to me. I know that it's cycles per second, and I can understand cycles per second. There's another very important reason for using this that we'll see very shortly. So this is the definition of the Fourier transform. I'm going to use u. I want to use u as the variable, the frequency variable here. So if t is in seconds, then u is going to be in cycles per second. But this turns out to also be applicable when we see Fourier transforms in different domains. So t could actually be a spatial dimension. It could be in meters or something like that, in which case u is cycles per meter. And we will explain more what that means when we get into that topic. But as electrical engineers, we're used to thinking in terms of time. And we're used to thinking in frequency and hertz and seconds. But it turns out that Fourier transform is more ubiquitous than just application to time. Now, we use this as a shorthand notation. We always put the x of t on the left and the x of u on the right. So this notation means that x of t has a Fourier transform of x of u. That's what that notation means. It's very, very simple. One of the other reasons that we use u instead of omega is the inverse Fourier transform. And here's the inverse Fourier transform down here. Now, if you remember, if you use an omega, you had to put a 1 over 2 pi out in front. How many remember that a little bit? There's a 1 over 2 pi. You have a lot of bookkeeping to take care of. If you only use u, you don't have to worry about those 2 pi's. It's much more beautiful. And one of the things that we're going to do is develop a language. Lord Kelvin said Fourier is a poem, a mathematical poem. So we're going to try to develop the tools to make it as transparent and easy to understand as we possibly can without all of the bookkeeping that is normally required of it. And that bookkeeping includes keeping the 1 over 2 pi out of the relationship. So that's the Fourier transform and the inverse Fourier transform. You notice that I've stated the inverse Fourier transform without proof. It's proved in the book, and maybe we'll prove it later. We'll see. But again, the beauty of it is the symmetry. Fourier transform is e to the minus j. Inverse Fourier transform is e to the plus j. That's all you have to remember. No 1 over 2 pi's to keep track of. This leads us then into, once we define the Fourier transform, into the Fourier series. Now I'm going to define this in a little bit more sophisticated manner than you are used to. You've always seen a periodic signal, or you've all seen a periodic signal. And the periodic signal is, man, I don't know why I go down all the time. I don't want to go down. I want to go straight. Trying to quit drugs here. I want to go straight. Okay, maybe I'll just do. I'll just do the best I can. Oh, there I'm doing it very well. Okay, we all know what a periodic signal is. We have an x of t, and then we have a period. And this period extends over an interval of t, and here we're talking about a function of time. And then we take a cookie cutter, this is capital T, and we cut it out like this. And so T, as we said before in defining a periodic function, is the period of the signal. Now, here's something interesting. Suppose that I took the integral over one period from here to here. In other words, I computed this area. Would this area be the same as if I went over here and started here, went over a period capital T, and I took the area over here? They would be exactly the same, wouldn't they? So no matter where I compute the area, it doesn't matter where I start and I stop. So for this reason, we adopt this notation. I want to integrate over a period. And the period can be anywhere I want to. That can be from minus tau. It starts at some value of tau, say tau here, and goes over to tau plus t at this point. So it just has to be over a single period. But it doesn't matter where that period is. Doesn't matter where that period is at all. And so that's what the notation we're adopting is. And this is very interesting. So let's go down to the Fourier coefficient. The Fourier coefficient, if you remember, is given by this expression. Now notice I'm not confusing the notation a lot with omega sub n's and harmonics f sub n's. We're just going to keep everything as a function of capital T. T is our one parameter. T defines the periodicity. It defines the frequency of this of the periodic signal. The frequency is 1 over the period. It's very simple to figure out. Now, here is the interesting part. Now, x of t is periodic with a period of t. Do you agree with that? That's by definition. This e to the minus j 2 pi nt over t is also periodic with a period of at least t. Sometimes it might be t over 2 or t over 5 or something like that, but it can also be a function of t. The point is if we multiply two periodic functions together that have the same period, are they also periodic? Yeah, if we multiply two periodic functions together, they're still periodic. So the point is that this function, the product of these two functions, is still periodic with a period of t. Because it's periodic with a period of t, it doesn't matter where we integrate. We just have to integrate over a single period. So that's the reason I'm saying that the Fourier coefficient is 1 over t times the integral over a period, and this period can be any period that we want to. It can be from 0 to t. It can be from minus t over 2 to t over 2. As long as the total integration is over a period, we get exactly the same result, because as we saw up here, it doesn't matter where you start and stop. The only thing that matters is that you go over a single period of t. So this is the Fourier series. I'm hoping that you've seen this before in one way or another. This is the way we are going to define it. Any questions? Okay, next slide. This is something also interesting. We're going to do something. We're going to go up here and we're going to take the periodic function. And this periodic function is x of t. And we are going to take one period of it. It doesn't matter where the period is. Let's take this period. And again, because we only have to integrate over one period, it doesn't matter where we do it. But right here is one period of the periodic function. I don't know where all that high frequency come from. Just ignore it, okay? And we're going to call one period of this x sub t of t. This is just equal to one period. Is that okay? So you can see that one period defines the periodic function, and the periodic function likewise defines one period. It's kind of easy to do. So here's the definition of x of t. It's equal to x of t over any period, and it's equal to 0 otherwise. That's what a single period is. Now, here is the interesting part. Let's go back to our definition. This was on the previous slide. This is how we compute the Fourier series coefficient. C sub n is equal to 1 over t times the integral which is shown. But notice, this is the same thing as the integral from minus infinity to infinity of a single period. Why is that? Because when we multiply this single period times this e to the j, everything outside of the period is set to 0, isn't it? Everything outside is set to 0. So therefore, we can integrate from minus infinity to infinity, recognizing that most of this integral is going to be 0, except where it is in the middle. Well, this is really cool. Do you know why this is really cool? Because this is exactly the term of a Fourier transform. Let's look at what the difference is. If we have e to the minus j 2 pi ut, that's what a Fourier transform is, right? Right? Here, we have exactly that same result, except that u is equal to n over t. Right? If we go over here and we say n over t is equal to u, we get exactly a Fourier transform. So this is exactly a Fourier transform, but it's not evaluated at u, it's evaluated at n over t. So it's 1 over t times the Fourier transform of a single period divided by n over t. This is kind of cool because it says we can find the Fourier series coefficients if we take a single period of the periodic function, we Fourier transform the single period of the periodic function, and then we sample it at intervals of 1 over t. Those are the Fourier coefficients. And you probably haven't seen it this way, but it's very nice. It allows you to figure out things if you just know Fourier transforms. You don't have to crank all those integrals. So it turns out to be very nice. So again, C sub n, let's summarize here. C sub n is equal to the Fourier transform of a single period sampled at n over t. And then you have a 1 over t thing out here. So that gives you the Fourier series coefficients. Now, if you look at this, I find this amazing, that it doesn't matter where I take the t. For example, suppose that I chose the x sub t to be here. I'm going to try to draw it nicely. Do you see what I'm trying to do? I'm trying to draw a period of this over this interval as opposed to over this interval. And this is a different x sub t because I've chosen a different period, haven't I? let me let me say again why I think this is amazing. See this periodic function here? You can take a single period right here, right? Or you can take a single period right here. And those are both examples of this x sub t, because it can be over any period that you want to. The remarkable thing is, if you take the Fourier transform and you sample it, it doesn't matter which one it is. Do you find that remarkable? I do. I find it remarkable. You can prove it with the math that it is indeed true, but it doesn't matter where you take the sample or where you take the single period. If you sample the Fourier transform, they're all exactly the same. It's really a remarkable feat. They're not the same before you sample, but after you sample, they are the same. Very, very curious result, I think. So with that, let's review, if you recall, Parcels Theorem. You have seen Parcels Theorem before. And Parcels Theorem says that the energy over a period is equal to T times the summation of the magnitude squared of the Fourier series coefficients. I hope you've seen this before. Can I assume that you have? Okay, I'm not getting a lot of exuberant responses. You haven't seen this before. Well, it turns out that indeed it's true. And I think that it would take us too long here and to derive this, but this is something which is known as Parcels Theorem. So this literally says how much energy is in the harmonics of each one of the components. So if you have a period which is x of t, how much energy is in each one of the harmonics? For C sub 1, that's the fundamental, the energy associated with C sub 1 is equal to C1 squared. The energy associated with the second harmonic is C sub 2 squared, etc. And if you add all these up, what is C sub O? C sub O is the DC value, correct? That's the DC value, so that's a squared also. And if you sum all these up, you get the total energy. So the C sub n's are equal to the energy in each of the harmonics of the Fourier series, and hopefully you've seen that before. Okay, whoops, going the wrong way. Convergence. Here's an interesting historical fact. How many have heard of the Michelson-Morley experiment from physics? It was instrumental in defining relativity. Michelson and Morley at Case Institute of Technology set up an interferometer called the Michelson interferometer and showed that the speed of light did not change in accordance to ether. They used to believe that ether was the thing which was floating in space, and they needed ether. Why do you need ether? Because electromagnetics needed some medium in which to propagate. Acoustic waves need air or matter in order to propagate. Heat waves need matter. So shouldn't electromagnetic waves need some medium in which to propagate? Well, they used to hypothesize it was ether. And in fact, it was the ether that defined the zero relative velocity of the universe. The whole universe was sitting in this ether, and this ether wasn't moving. But if we had this ether, we should be able to detect the we should be able to detect. How come I'm not the main person? David, you're the main person. Are you seeing me? Okay, everybody's seeing me. Okay, well, I see David. Maybe I don't want to see me. Okay. Well, anyway, the idea is that if it was ether, then you would have things like Doppler shift. You know, like a car goes by and goes as it goes away from you. It's the same thing with the speed of light. They used to think that if light was coming towards you, it would be coming at you faster than it was going away. So Michelson Morley set up this experiment at Case Western Reserve where they did an interferometer, and their idea was to show that indeed this ether exists, and that the speed of light in the ether with the Earth going in one direction would be different than the speed of light with the Earth going in the other direction. We would have this this Doppler shift. And they found remarkably that that wasn't the case. This was the experiment that allowed Einstein to conclude that light, the speed of light was independent of any frame of reference. And that was that was a big deal, and that was one of Einstein's axioms. Well, Michelson was also a really brilliant experimentalist. He did this with his experiment at Case Reserve. And one day he decided that he would build himself a mechanical system to compute Fourier series. Could you come up with a mechanical way to compute Fourier series? I don't think I could, but he came up with a way to compute Fourier series. And then he found out something. He found out that it didn't work the way he thought it would work. What he found out was that you had this sort of phenomenon. And you can see what happens. And the troubling part was not that it didn't converge, but you see those little rabbit ears? You see those little rabbit ears on top of the square wave? Well, this was for a finite Fourier series. Instead of summing over all of the values of n from minus infinity to infinity, you just summed over a finite number of them. And it kind of looks like Batman, doesn't it? This is with n is equal to 10. This is with n is equal to 25, 50, and 100. This is Batman. This looks more like Bart Simpson, doesn't it? And what he found out was something very interesting, is that these rabbit ears, they got smaller and smaller, or they got more and more narrow, but they never disappeared. They always were up there. And so they got smaller and smaller and smaller, but the height of them never went away. And Michelson said, boy, I screwed up. I don't know what I did on this mechanical apparatus. And so he published his results and said, can anybody help me? I don't know. He published what he did, I guess. And he told people that we have these rabbit ears. And there was a mathematician that looked at that and responded to Michelson and said, I know what the problem is. And he gave the math for it. Can anybody guess what that mathematician's name was? Gibbs, yes. If you've seen this before, you know this is called Gibbs Phenomenon, that the Fourier series does not converge point by point. You have problems with the convergence at the points of discontinuity, where that square wave goes up. Do you remember Laplace and Lagrange said, I don't believe that you can capture those things with sinusoids? They weren't exactly right, but they were kind of right, because they anticipated the Gibbs phenomenon, that there was something wrong with estimating a discontinuity with a bunch of sinusoids. So they didn't go away. So that is the problem with the Gibbs phenomenon. Now, the way that we do this now, how do we say it converges? There's actually different types of convergence. And one of them is mean square convergence. This does not converge pointwise. It doesn't converge pointwise where there's rabbit ears, where you have Batman and then Bart Simpson. It doesn't go away. And so it turns out that the following is true. If you integrate over a period of x sub n of t minus x of t. So this is what you get. This is what you want. And you integrate over this and you take the limit as n goes to infinity, then you get 0. And so this is called, again, mean square convergence. Now, how does this work? Well, if I were to ask you, I have a function here, and this function only, here's time is equal to 0, here's time is equal to 1. At time is equal to 1, we have a single point, which is 3. Not a delta function, but a single point that's equal to 3. What is the area under that signal? If it's a continuous time signal, the area is equal to 0. Because we know that area is, well, integrals are areas, and this thing has a height of 3, but it has a width of 0. So it has 0 area, or a measure 0 is what the mathematicians call it. So it has no area. So that if the square wave converged to something that looked like this, where we just had a couple of points disconnected, its integral would be the same, even though there would be a few dislocated points. And so that's the way that Fourier series converge. They don't converge at every point, but they converge in the mean square error sense in the way that I have it shown here. And there's a whole bunch of different ways to talk about convergence, but that's beyond the scope of what we want to talk about. So this gets us now into the Fourier transform and different ways to manipulate the Fourier transform. These are tools for our tool chest. The first one is the derivative theorem. The derivative theorem says if you differentiate a function n times, that's the same thing as multiplying it in the frequency plane by e to the j2 pi u, and this shouldn't belong here. I don't know where that came from. And this can be very easily derived by looking at the Fourier transform, or the inverse Fourier transform. Let's see, I don't want to do this. I want to do the inverse Fourier transform. So here's the inverse Fourier transform. Are we good? Now what I want to do is take the derivative of this. Let's just do one derivative. I think the general case will be true. The derivative of the left side is equal to the derivative of the right side. Is that correct? The answer is yes. Now, here's an interesting question. Can I take that derivative side inside the integral? The answer is yes. Can I take it past the x of u? Yes, I can, because it's not a function of t. The only thing that's a function of t is this. Now, mathematicians might have a hard time of commuting operators such as derivatives and integrals. We don't. We're going to sacrifice some of the rigor for intuitive understanding of what goes on, and we're going to be able to take the derivative inside the integral sign always. So never worry about changes of that sort. That's no problem at all. So this is equal to the integral over t of x of u times the derivative of the kernel and of course we see that this comes down as the integral over t, and I'm going to lump everything together as a j2 pi u times an x of u e to the j2 pi ut.
It's an integral du, so why do you say it's an integral over t?
I misspoke. It's the integral over u. So I think you could see that this is a Fourier transform. This is the Fourier transform of everything in the bracket here. It's the Fourier transform of this because it's this times the e to the j2 pi ut, and it's the Fourier transform of this. So we conclude that the derivative here has a Fourier transform of j2 pi u times x of u. Is that okay? So that's the derivative theorem. You can see that this can be easily extended to higher dimensions. Now let me ask you this. If you take the derivative, say of an image, and you take the first derivative of an image, what does it do? It accentuates the edges, doesn't it? I don't know if you've ever gone into into image processing and taking an edge, but it accentuates the edges. Anytime you have an edge, you have a very high derivative, don't you? If you have a signal which is coming along and bloop, it goes up, right? There's a high derivative. So therefore, if you have a edge to a signal, that's going to be a very high derivative. Well, notice what this does, this j2 pi u. It takes the original signal and it multiplies it by a j2 pi u. And if you take two derivatives, it's u squared, right? So what are you doing here? You're amplifying the high frequencies, aren't you? You have the Fourier transform and you're amplifying the high frequencies. So anytime you have a high frequency, that is really accentuated. And what do you do to the DC? The DC is totally wiped out, isn't it? It's multiplied by 0. So this is a manifestation of the Fourier transform then. Okay? Any questions on this?